so it would be 109.5 degrees. However, if you add a lone pair and remove an atom, you remove a hydrogen for the example, you're going to be decreasing the amount of bond angle in here, so it would be less than 109.5. And if you add another lone pair, so there's two lone pairs in total, which is this one and this one, it would be even less. Technically, it would be lesser than this value right here. So if you keep on adding lone pairs, which is this, in this case, I don't think it's possible because you only have like two atoms left that are attached to the central atom, then it would be even less. So in this case, for 5, you have 5 outer atoms connected to one central atom. So it's like that. You're going to have pretty much predictable bond angles. Where did I write that down? So yeah, it says here, higher amount of lone pairs equals lower amount of predictability. And it says here in the problem, it says like, where is it? It says smallest predicted bond angles. That basically just means least predictability, which means like, that's not even related to our problem, but whatever. Least predictability means like the more amount of lone pairs you have, the less predictable it is. And that, by that I mean, like, for this it says tetrahedral. The whole group is tetrahedral in electron geometry. However, this is the most predictable to be tetrahedral because it doesn't have lone pairs. In the case of 5 and 6, the more lone pairs you have, the lesser the amount of bond angles. However, if you have 3 and then leaving you with 2 outer atoms, that would turn to linear. And that would also be the case for this, where you only have 2 outer atoms. That would also be linear. So it does decrease, except for like this part right here, which is because it becomes like 2-dimensional in a sense, because it's just one square over a plane, like just like this shape right here. So it's that's like one of the exceptions, but yeah, it's weird.